Okay, so rather than cover these last couple pages in class, I figured I would just do a video. So first thing we're going to talk about is Z-scores. You guys watched a video about Z-scores almost a week ago now on that one JITT assignment where you watched that really monotone guy talk about Z-scores for a very long time. So you saw the calculation there. Only thing I want to tell you now about this calculation is it's going to be given to you on the exam. So you don't have to waste space on a note card putting this down. The form that's going to be on your exam is this last one here that uses the parameters, mu to represent the population mean and sigma to represent the population standard deviation. So that's what you're going to have on the exam. How I normally like to test this. First off, we might have some sort of conceptual question. So you really need to understand what a z-score represents. And that is that the z-score tells you how far above or below the mean you are in terms of standard deviations. So if you had a z-score of 3, that would mean you are 3 standard deviations above the average or above the mean. And a negative z-score, a -3, would mean that you're 3 standard deviations below the mean. This here allows us to use z-scores to see if something is unusual. We had a rule in the standard deviation section that told us most data, right, is within 3 standard deviations of the mean. So that alone really tells us that if anything is outside or close to a z-score of 3, that's going to be unusual because it's right at the cutoff of where most of our data should be. And you could even look back at that histogram that I had back in the standard deviation section. So first thing we're going to do is show how we can use this to evaluate outliers. So the first example here says blood glucose levels are normally distributed. This is usually a nice key to tell us that we can use these rules that we have about standard deviation and mean, especially the one that most of our data is within 3. And then we're told that it has a mean of 85 and a standard deviation of 5. It says, would a patient with a blood glucose level of 68 be considered unusual? So this 68 here is an observation from this distribution of blood glucose levels. So we've got all of this information. And the first thing we're going to do is go ahead and copy down our formula. Our z-score is x minus mu all over sigma, our observation minus our mean divided by the standard deviation. And this is going to give us 68 minus 85 because our observation is below the mean. So we're going to have a negative difference here. And this is all over our standard deviation. This tells us exactly how many standard deviations we are below the mean. So if we work this out, we get that our z-score is -3.4, which would imply that this is, yes, unusual, especially by that 3 standard deviation cutoff, which is easily the most conservative. Another very commonly used cutoff is 2. So this is unusual by both the 3 standard deviation cutoff and, of course, the 2 standard deviation cutoff. So that we can sort of visually see what the hell this z-score means, let's think about our normal distribution. Normally distributed, remember, it means it has a bell shape. It's unimodal. It's symmetric. If something is symmetric, that means the mean is, well, smack dab in the middle, right? So our mean is at 85. Now, these standard deviations, we know from the standard deviation section that most of our data is within 3 standard deviations of the mean. So I'm going to make 3 little bunny hops out to cover up pretty much my entire distribution. And for each of these bunny hops in the forward direction, I'm going to add standard deviations to move forward, and I'm going to subtract standard deviations as I move to the left. So that'll be able to give me my different blood glucose scores along this distribution. So up to 100 would be within the usual range if we're using the 3 standard deviation cutoff, and all the way down to 70 on the low end if we're using 3 standard deviations as our cutoff. And you can actually see where 68, did I make that 700? Crazy. You can see where our 68 would have fallen on this. 68 would be way past 70, right? Which is why we are 1, 2, 3, and 0.4 standard deviations below the mean. That is what this demonstrates. So if you're going to answer the question at hand, the answer would be yes, because it is more than 3 standard deviations below the mean. Boom. Right? So that's what we're going to do. Now you can go ahead and do this math again for 98. I think it's overkill at this point. If you want to double check your math using a calculator, that's my one recommendation here. A lot of students, when they go to enter this formula in the calculator, they type it in this way, and they end up getting in trouble because the calculator will do that division first, knowing the order of operations. So if you want to do this in one line in your calculator, just make sure you have parentheses around the numerator. Otherwise, press enter and then divide by 5. So the other use of a z-score is to compare apples and oranges, for lack of a better analogy here. You can imagine that for admissions for college, there are 2 different entrance exams you could take, the ACT and the SAT, and they're on very different scales. So if the entrance people, the admissions people for a particular college, want to compare someone who took the SAT to someone who took the ACT, they need to be able to put them on the same scale. And that's what z-scores allow us to do. So that's another use of them. So we have this example here. Your friend is taking stats. They scored an 87 on the first exam, well, you scored an 83. So right off the bat, you're going, oh crap, my friend is better at stats than me. They had a higher score, right? They got to be almost plus and I got to be almost minus. But turns out once you get a little more information, the class average for his was an 80. So his test was a little easier because your exam has an average of 70. Has an average of 70. So this is one of those instances where z-scores would be very useful. So let's go ahead and just kind of collapse all this information that we have. So his class, we know his observation, his actual score is an 87. The mean for his class is an 80, and the standard deviation is a 5. Versus your class, your observation, your score was an 83, the mean was a 70, and the standard deviation was a 10. So, looking at this, you might simplistically just say, well, look, he was 7 points above the average. I was 13 points above the average. So obviously, I did better than my friend. But again, what matters here is your standard deviation. His values were a lot less spread out on their exam versus our values, which apparently I wrote an S, with a standard deviation of 10. So again, just because we're really learning this, I'm going to go ahead and draw out the curve. This is absolutely unnecessary on a test, but we might as well try it now. I am going to run out of space on that right one and pay for it, but we're going to try it. Let me redraw it. Really tiny. Okay. So again, we're assuming a normal distribution here, so our mean is smack dab in the middle. For his class, it's much higher than yours. And for both of them, we're going to do our 3 little bunny hops, or 3 standard deviations out to each side. And remember, that's just a rule about standard deviations. So, for his class, we're going to be adding 5 each time and subtracting 5 each time to the left. Whereas for your class, you're going to be adding 10 because your standard deviation is larger. So 80, 90, and 100, and 65, 60, and 55. Assume we can read all of that. Now let's look at your guys' scores relative to your class. He got an 87. 85, 86, 87 is right about halfway between 85 and 90, right? And your 83, it's a little bit closer to less than halfway between this 80 and 90. You are both 1 standard deviation and some change above average. So we really need the z-scores in order to make this fair comparison between his score and your score. So let's go ahead and calculate that. I'm going to go and erase these since we don't really need them anymore. Oh, a little too much. Okay, so our z-score formula, again, z is our observation minus our mean divided by our standard deviation. We're going to do that same calculation for both you and your friend. So on the top, we're going to end up getting that 7 points difference that you saw, and we're just going to figure out how many times 5 goes into 7. This is where that definition of a z-score comes in. So our z-score for your friend is 1.4. You, on the other hand, 83 minus 70 all over 10. You were 13 points above average, but your standard deviation was 10, and 10 only goes into 13 1.3 times. So in this case, your friend did better on the exam because their z-score, they were more standard deviations above the mean than you were. So your friend did better. You both did good. You both were above average, but he did better. So I want you guys to go ahead and take a moment, if you can, pause the video, pretend we were in class, and work on this exercise, all right? Definitely put one of these on each class. It looks very similar to this. I usually say explain using z-scores why this is true. So pause the video and do that. I'm going to jump right into it because I'm assuming you've already paused it, worked through it, and are now checking your work with me. Okay, so we got 2 guys training for the Boston Marathon. We can see we have 2 guys. Their times follow normal distributions for both these loops. We have a hilly loop with our friend James, and we have a flat route, which Rob is training on. And we are told all that good information that we need in order to calculate a z-score. For James, we were told that the general population has a mean of 167, a standard deviation of 25. Rob's thing with the flat route, we were told the mean was 143, the standard deviation was 20, right? All I'm doing is grabbing this sort of information, mean, standard deviation. And then we were given their actual observations. James takes 91 minutes and Rob takes 86 minutes. And this is one of those questions where I always ask students, are these guys good runners? And everyone says, yes, they are finishing this a hell of a lot faster than the average. And for running, faster means smaller times. So keeping that in mind, let's go ahead and calculate our z-scores. Observation minus the mean divided by the standard deviation. And observation, if you want, you can use a little subscript for James and a little subscript for Rob. I do not care. If you don't like that, you don't need it. We're just going to go ahead and calculate both of those. So it looks like for James, we've got a z-score of negative 3.04. And for Rob, we have a z-score of negative 2.85. So who is the better runner? Based on all this information, James is the better runner, right? Because he is further below average, and we want to be smaller when it comes to running times. His running time was further below average. And this is something that's very important, is to note that better, you do need to make sure bigger is better if you're using z-scores to compare two things. So moving on to the last couple bits here. We have a section about outliers. We've spent the last bit here using z-scores to identify outliers, using the fence formulas for box plots to identify outliers. And basically, what do we do with outliers? The answer is we make sure we comment about them. It says do not leave them in place without comment and do not drop them without comment. So if we're going to throw out people, which I've done in previous studies, because of blood glucose levels that were far, far, far above and below average, you just need to make a comment about it. We excluded these people because of this and have a good reason for it. Excluding them, though, just because they're unusual is usually a bad practice. I've got a nice funny comic here. I strongly suggest you read it. XKCD is amazing. And it's got a box plot in it. So now you guys can get these high-level stats jokes. And the last piece here are time plots. Just a different way to look at a quantitative variable.